pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
All right, welcome everybody. Thank you for coming, and people on the video in the future when you see this. My name is Michael Wong, and along with Maggot Michael, this is a session that's going to be talking about what is coming in Concurrency TS2. And although we have presented this before, it's always been in an incomplete form. And this is the first time we're going to be able to present to you all the different features that's in Concurrency TS2. That's why the subtext here is, at last, it's going to Geneva, because we still have to do that weird thing where after we wrote it, we published it, we edited, and that was like in April and May. Somebody still has to walk the paper over to Geneva, and then they have to come back, probably, as far as I know, like in December, before it will really be published. But as far as we know, nothing is going to stop it now, pretty much, short of the end of the world, I suppose. So that's why the title of this is Concurrency TS2, at last going to Geneva. Now, just to set the stage, you might ask, well, what happened to Concurrency TS1? Well, Concurrency TS1 happened in the C++, just after the C++ 17 time, or during the C++ 17 time frame. In 2014, 2015, you see that deep green bar at the bottom of the top diagram? That's when, and in it, there were things like future, stood future. There were things like latches and barriers. There was atomic smart pointers, okay? And many of these have already made it into the C++ standard for the most part, okay? And then after that, then we started the second version of the Concurrency TS, which we call 2. And it's been going on since 2021 through 2023, and finally completed at just before the end of June. And that is now going to enter now. I don't have a dotted line because I don't know where it's going to end up because of the vagaries of ISO, but that's how it is. If you're wondering what is a TS, just a quick diagram on the right that ISO shows to people. A TS stands for technical specification. I'm going to push you right into the middle, like step 3. The first step is just like new proposal, preambles, and things like that. And you have to build consensus. Then the TS enters in a mid stage. But what happens is that it's different than an ISO draft. An ISO draft goes on and becomes a DIS, a draft in the national standard, and then a final draft in the national standard, step 5. And then step 6, and that's what C++ 23 is going through right now. And a TS doesn't necessarily need to go through all those stages. It gets a common period, which is what happened already, okay? And then now we're in the last stage where we're in what's called the PDTS, where essentially there won't be any more. I'm trying to think, will there be any comments? Actually, there still might be comments, actually. So there will be one more round of voting, yes, before it gets finally approved, okay? So that's where we're at right now. All right. So what's in the Concurrency TS2, now that it's on its way to Geneva? So TS2 was closed in 2023 in paper N4956, and because it's an official ISO document, it gets an N number as opposed to a P number. That's the difference. All the P number papers are internal WG21 papers. They don't go to ISO, okay? In our previous talk last year, we've already pointed out that we would have deferred reclamation. Those 2 initial papers were already there. So those are hazard pointers and read, copy, update. My colleague, Maggot Michael, is going to talk about those. And then since then, in the CppCon meeting in 2023 and in the Kona meeting in 2022, we added 3 more papers. One is asymmetric fence. The other one is synchronized values. And then the third one is bitewise atomics. Now, it will usually take a few years for experience to gather. Once it goes to publication, it will take a few more years for experience to be gathered and give you feedback on it. So it's quite possible they will miss C++26, except RCU and hazard pointers. They will not miss C++26, even though they're far bigger and far more interesting and complex. Because why? Because we've already put them into C++26. And that little story is going to be, stay tuned, and we're going to talk about that. Maga's going to come and talk about hazard pointers and RCU. I will come back and talk about the other three items. So just to give you an overview, what are they good for? For hazard pointers, RCU, and asymmetric fence, they are fantastic for low latency. If you're into like, high performance, high frequency trading, even in some cases games, they've already have found a lot of uses through them. And in a way, this is why two of them have already entered 26, is because they've already have a lot of usage experience. The other two, synchronized values and bitewise atomics, are fantastic for safety and convenience. They basically are wrapping something that you can already construct yourself, but we're going to wrap it and just make it an object and make it so that you can't forget to unlock it and things like that. Okay, that's it. So now I'm going to ask my colleague. I believe the next slide is. Thank you.
Thank you, Mike. Hello, everyone. I'm going to start with just overview of deferred reclamation. The goal is to protect dynamic objects that may be removed concurrently, like being accessed and then get removed concurrently, from being reclaimed prematurely while it is being accessed. So why do people use that? Sometimes like, oh, well, why would you expose that kind of pattern of access? The main reason is for less synchronization, lower latency, lower contention, and so high throughput. Read, copy, update, and hazard pointer, they can replace slower, less scalable synchronization by doing deferred reclamation, not doing the reclamation right away when it is reclaimable. By doing that, we can gain in the performance. So to give you a flavor of the performance, at least in the Folly library, open source library, RCU, the constructor, destructor, and protection of a segment of code takes about like close to 3 nanoseconds. Hazard pointer, constructor, destruction, protection, in the best, of course, let's assuming hot in the cache and like, best case scenario. But yeah, no, it's all no atomic operations, all that is about 4 nanoseconds. Hazard pointer, if you don't need to construct and destroy it over and over, if you hold on to a hazard pointer and just use it for protection, then the protection is half nanosecond. And then the scalability, all these operations they are writing locally or private, something private or local, not private, but read single writer, multi-reader, and they don't write anything globally. So then you have basically perfect scalability. Okay, let's look at what are the kind of the general options for safe reclamation. So the two more conventional ones, and these are not deferred reclamation, they are immediate reclamation, are using read-write locks, like shared mutex, for example. And this is not about just reading and writing, it's more about access and removal. These are kind of the things that we're trying to protect against. Or reference counting to say, okay, as long as you're accessing something, you're holding a count, a reference count, and then that prevents the reclamation from happening prematurely. Then RCU and hazard pointer, they are kind of, we'll see that there are similarities there in their use cases with the read-write lock and reference counting respectively. they are deferred reclamation techniques and faster. So read-write locks in RCU, they protect segments of code. They protect everything that is protectable. So they are, it makes them easier to use, but also they protect everything so that they can hold up reclamation. Well, in the case of locks, they would hold up updates. You cannot really hold it for long. In the case of RCU, would be holding reclamation. Hazard pointer and reference counting are more suitable for long protection, but need to be specific. So these are kind of like trade-offs, and these are all tools that complement each other. As I mentioned, hazard pointer and RCU, they defer reclamation. Locks and reference counting, they reclaim immediately once something is, in the case of locks, they know that they can reclaim right away. In the case of reference counting, they reclaim when it is safe to do so, when it is immediately after that. So looking at this table, this summarizing some of these trade-offs, you can see the two on your right are the deferred reclamation techniques, and they have some kind of similarity to the two on the left in where they're applicable, what are the characteristics. So in latency, yeah, you know that the conventional ones, they do atomic instructions in their fast path. In RCU and hazard pointer, you don't have any atomic instructions in the common path. For protection, I'm talking about protection. You're doing, of course, the reclamation. That's a different story, and it doesn't happen as frequently as protection. In terms of contention, locks and reference counting, if you have multiple readers or accessors to a shared object, they're going to contend with, they get in each other way. They're writing to basically share data, whereas the ones on like the RCU and hazard pointer, they're just writing locally and not interfering with each other. Protection duration, the reference counting and hazard pointer are similar in that you can hold on to them as long as you like. They are only, in the case of both of them, they only prevent the reclamation of what's being protected specifically. Whereas locks and RCU, they are protecting everything, so you cannot keep the protection for long. The lock, because it will cause deadlock or preventing or blocking the updates, or whereas in RCU it will just prevent reclamation. How many, the number of objects not yet reclaimed, of course, because it's immediate reclamation, the locks and reference counting, it's zero. There's nothing that is kind of you're keeping around that could be reclaimed, but you don't reclaim. So that's kind of, these are cleaner semantics. Whereas deferred reclamation, you have to be extra careful, and there are remedies for that. I'll talk about it briefly. But yes, it is, you think that you remove something, but okay, it's not reclaimed yet because it's deferred. In the case of hazard pointer, you can bound the number of objects. So it's kind of even like, no matter what, you have a bound on the number of objects that are not reclaimed. There are theoretical bounds and practical bounds, but the practical one is basically you have a number of hazard pointers in the process. Then for amortization, you would keep around unreclaimed objects that are proportional to that. So that's kind of the expectation. It's kind of the linear and equal to the number of hazard pointers, basically. Okay, irregular protection. The ones that protect everything are better at irregular protection because it's simpler. Whereas the others are really, you have to be, that's kind of error prone, and you have to be very careful in deciding what exactly you need to protect. So if you're, if the structures are regular, that's okay. But if you're like you don't know what is the relation between the objects or the flow between them, then okay, it gets more complicated. All right. Actually, let me. All right. So this is a motivating example using read-write lock for an object that is accessed frequently and updated infrequently. So, so here we use like a shared lock. You want to have multiple readers concurrently in parallel accessing the same object. In this case, they are holding a reader lock. They read the they get a reference to the object from some shared source, and then they do a user function. We can say arbitrary function, but it's going to be limited because we're using a lock. So on the other hand, for an update, they're going to acquire a write lock. They're going to replace the object with a new one, and now they can delete it right away because, well, they're outside the lock, but the decision to replace it is inside the lock, so they know that nobody has reference to the old object. This is like slower than what we'll see later because it's doing atomic instructions. Readers are blocking writers, and writers block readers. And the user function, it's not quite arbitrary because it's holding the reader lock. So you're not allowed to block too long or take too long. You're not allowed to call the update function because it's going to deadlock with itself. Let's look at something also conventional using reference counting. So in this case, using atomic share pointer. So the source is an atomic share pointer. The read access, okay, you just like load that share pointer, and now you're protecting that object while you go do execute the user function. You can take as long as you want. You're protecting the object. You're not preventing anything. You're not holding locks. Okay, so that's the advantage of that. The update part is that you're replacing the share pointer with a new share pointer. Again, it's not blocking anybody. But then it's slow. You're going to do atomic instructions. We saw a talk like this by Daniel Anderson doing like 2 atomic instructions, improving over like the split counting is like 6 atomic instructions. So anyway, and if you have contention, you're going to be you'll be doing atomic instructions on the same reference count. So it's scalability is going to suffer a lot. But yeah, readers don't block writers don't block readers. You're free to the user function can do whatever it wants really. Take long and call the update. All right, so let's look at the proposals. Now we're going to dive into RCU, and we're going to look at the same motivating example, and now using RCU. So in this case, we changed the source to be back to being an atomic T star, but then the class T, in this case the interface is intrusive, so it's going to inherit from a class template called RCU object base. That's like it's like the objects that are protectable by RCU will inherit from that. So the reader part, they're gonna, this long incantation, basically it's starting an RCU reader section. But for convenience, it's using the locking interface, so that's why it's doing all this like RCU domain. That's not really something you can change. It's just like this is the way to express it that in a way that uses the locking interface. So once you start that, you're creating an RCU reader. So you're constructing an RCU reader. That's all local. Thread local operations, and now you're protecting everything that is protectable by RCU, like the objects that inherit from that class template. You can call the user function, but you have to be careful with the user function. You cannot take too long because you're preventing reclamation. Update, you're gonna atomic exchange of the the old object with the new object, but then you cannot delete the old object because someone might be using it. And instead of that, you call a member function of that object base called retire. What it does, it basically are saying to the library, to the RCU library, take this object. You are now responsible for reclaiming it, but don't reclaim it as long as someone is already started an RCU reader section who may be using this, because we don't know which objects are being protected. Like, we know everything is being protected. We don't know what is being used. So that's why we're saying just wait until that scope lock is done. So this restricts the user function to, it's not allowed to take too long. It's not allowed to block, but it is allowed to call update, because it's there's nothing that prevents that. Okay. Oh, I'm not sure I'll hear you, but try.
So a class that inherits from RCU object base can only live on the heap?
Can someone, repeat the question, please? Sorry.
So a class that inherits from RCU object base can only live on the heap?
Normally they are on the heap, but there's no. Yes, I would say they have to be on the heap, because that is deferred reclamation, and you can say the same about shared pointer, and it's like the object that's being protected by a shared pointer, it has to live beyond like that kind of scope. Yeah. Okay. So anyway, this is kind of a typical use case of RCU. Any questions about this? Yeah.
What happens if you don't want to retire?
I can hear you. Sorry.
He's saying what happens if you don't call retire?
Exactly. Yeah. Well, that's then you leak the object. So this is like you have to call delete, you have to call retire. So it is you're paying. This is kind of you're paying that price of like you have to be careful to gain the performance that we talked about. Yeah.
Actually, I have one other question. So
Come over here.
Or tell Michael. Yeah.
So I'm just trying to understand what is the mechanism that is used to tie your pointer to the actual lock zone? So how do the two things retire? Because
the mechanism to assign what? I'm sorry?
The mechanism to actually tie your object source underscore to the actual lock zone. So how does it actually?
That's the thing about RCU. It's protecting everything. So you start this section, you say, I'm going to access protectable objects. Don't ask me what I want to protect. So the library has to like assume that I'm accessing everything.
Okay.
So you don't tie the object to the RCU section. RCU section is saying we're accessing protectable objects. Anyone of them.
So as long as there is any lock pending, the object's not going to be retired.
Nothing that's reclaimed.
Okay.
Like yes. Yeah. So that's why you cannot take too long in that section. Oh, yeah.
Yeah, I have a question. So if there's one thread or user is using the read and access for a long time, and there's another update, will the update will be deferred or locked, being not able to access update?
So the reader taking time, and then in the meantime there's update.
Yeah.
Right. It's no problem. It's gonna be a new object in source, but then the old object is just retired. It's not deleted. It's like you can actually use it and access it, and like you don't need to. You can the user function will just keep going as if nothing. It's not affected. Yeah.
Thank you.
All right. Okay. So yeah, I'm going to talk about the TS2 interface. Oh, sorry. Yes.
The retire is being the retire function is marking that order to be reclaimed later on. is the reclamation must be done in the same thread, or it can be deferred to be done in another thread, so it won't affect on the critical path?
If I heard you right, are you saying that the timing of the reclamation versus retire, like as in
The thread of the retire,
the thread of the
it can be done later on the reclamation in another
thread? That's one of the
thread?
questions that we ask in the TS process, and I'm going to tell you what, like in the standard is going to be quality of implementation unspecified. In practice, it's actually much better to have a background thread option, as an optional, whether it's opt-in or opt-out, because I mean, some applications say I can't have extra thread, or some applications like, yeah, sure, use extra thread because I don't want to be doing reclamation. It's like someone doing a DQ operation from a queue, and they're expecting to take like whatever, 20 nanoseconds or something, and then now they end up doing tens of thousands of reclamation. They don't want that. But yeah, thank you. Okay, so I'll move on to the API, and actually, this is the same interface for the. So in the case of RCU, it's like the TS went almost like identically to the IS. So this is like going to be in 26. Mainly it has a domain that is only used for RAII locking, as we saw in the previous example. And then the objects protectable by RCU, that's basically called retire. So it is quite simple interface. Oops, sorry. Yeah. So the objects are basically, that's the object base, and it calls retire. It has an optional deleter. Otherwise, it's used the default deleter. Then there is the singleton for the RCU domain. That is really, it's not custom domain. So RCU is not offering yet. That's one of the questions. Do you want custom domains? But what's offered is only one default domain. But it has to be exposed for the locking interface. That's why it's being explicitly exposed. Then you have free function for default. Then these free functions to manage the updaters. These are like you don't need. So the common user doesn't need to use these. But you have synchronize and barrier. These are ways to synchronously control when reclamation happens. So synchronize is actually saying, okay, we'll wait for another grace period where anybody who started a RCU reader section must have finished already. So that can wait for a long time. The use of barrier is different. It's more like saying if a callback, that if deleter has started, then let's wait for it to finish, in case it is kind of using a transient kind of module or a cached kind of functionality. Yep.
So my question is about the RCU default domain. If you only have one shared domain, so you're keeping one counter that is atomic across all the different types.
I'm not sure I heard you, but
Can you come over?
or Michael can repeat, or sorry, but
The RCU default domain that you have, it's a shared atomic counter across all objects.
no, it's actually just something that can lock. You're not even, the lock doesn't lock anything, so it's empty.
It's empty. Okay.
Yeah, I mean you may have some global, but it's really, it's not lock. You do lock on it, nothing. It's
Nothing
not,
happens, so it's basically
It's
a
actually
no.
okay. So what this gets translated to a thread local operation, and
Okay.
of course when you say synchronize, then now you're looking at all these thread local stuff, checking are you in a reader section or not, but you're not doing anything globally.
Okay,
So
so
yeah.
these are all thread local. Okay.
That's just the domain is really just something that you can say I'm locking the domain, but actually in effect I'm saying I'm doing a local RCU reader section.
Okay.
Anyway, I appreciate the questions, but I don't want to run out of time, and but go ahead.
One small one. Is recursive Okay. Like, can I take a lock and then take another
Yes,
RCU lock
yes.
on the same
RCU,
thread?
you know, so just yeah, because you don't sometimes you don't know if the user function is it itself using RCU. Yes. Okay. Thank you. Okay. So we'll need to hurry. Yeah. Okay. All right. So this is the interface, and I think this gets to the question, and this is what we want from the community: is like, you know, do you want custom domains, multiple domains? Do you want like a user supplied RCU domain, you know, RCU implementation? Do you want to like to poll? Okay, is this now grace period, or just like say synchronize and wait? Do you want user control over scheduling? Like you mentioned, like which do you have an extra thread and or the same thread? Do you want to specify that? Memory leak detectors. There are lots of questions that Paul McKinney put in the paper P2545. That's actually for the standard, but it has a lot of questions that the community would be very useful to provide in case that there are extensions of RCU. Okay, I think I'll have to hurry a little bit. For hazard pointer, let's see. The same example, but using hazard pointer, it's a different thing. Now you're not really having a section or anything. You're actually constructing a hazard pointer. That's the way to do it in this interface. Make hazard pointer. It constructs one. That's kind of like basically a couple of nanoseconds. Destruction is a couple of nanoseconds. And now the protection is saying, okay, here's a source. Give me a pointer from it that is guaranteed to be protected. Now you take that and you call the user function. In the case of hazard pointer, don't worry, you can do whatever you want in that function. It's not holding up anything other than reclaiming that specific object. The update, you do atomic exchange in this case, and you retire, you don't delete, because it's not safe to delete, but the library becomes responsible for the reclamation. Okay, so no atomic instructions, no blocking, allowed to do anything arbitrarily. So, okay. All right, any questions? All right, good. So this is the TS2 interface is different from the IS interface. So I'll tell you while we talk about it, what are the differences, so we can, you know, so keep in mind. This one has custom domains. But actually, my production experience, nothing. Nobody needed custom domains, so we didn't push it to the standard because we're only pushing what we know is very useful. Objects protectable is actually very similar to RCU. The object protected by deferred reclamation is identical interface effectively. The hazard pointer themselves, and I'm going to talk about that. Okay, so the domain, what we're offering is like customization using polymorphic allocator. So you can say, oh, I know that I will have only 40 hazard pointers. I want them to be laid out in the cache like this. And so you have your own allocator that will give you or you can say, oh, I want a bunch of hazard pointers, packed into a cache line, and so it's kind of, you can control that if you want. But by default would be just the default allocator. So that's the customization we're offering here. We want feedback. Is this useful? Do you need domain? But anyway, I'll talk about the questions in a couple of slides. And then there's a default domain, and there is, okay, this is important, the cleanup operation. This is doing synchronous reclamation. This is when you say, I want things to be reclaimed like now, and I'll wait for it. We remove that from the standard because there are alternative ways, and we want to know what is really, like some things that are lighter but much more efficient, because this is very expensive, the cleanup. All right. The objects, you can recognize retire. It is just retire. But because we have custom domains, we have kind of variants of it with like, do you have a custom domain or not? But that's, but it's just a retire, normally it's just used like without any explicit arguments. All right. All right. Okay, this is the hazard pointer, and actually, it's really a hazard pointer holder. It's not really the hazard pointer itself, but it's cleaner to call it hazard pointer. What it does, it's a control. You own it. It owns at most one actual hazard pointer. A hazard pointer is really just a pointer, like pointer-sized pod or what, So it's kind of, but this is kind of saying so it could be empty. And the committee insisted that even though the default is usually we're actually constructing a real hazard, an actual hazard pointer, but it said if you have something by default, then it should be empty. So this is kind of rarely used, but it's very useful to have an empty hazard pointer. That's like the default. Okay, the most important operations are protect. This is the one that you would use most commonly. That's the one we say, give me a shared source, atomic source, and I'll take from it a pointer to an object that are guaranteed to be protected as long as we don't change the hazard pointer. Okay. There's try protect where you say, okay, I read something, but I'm not sure it's protected. Can you check for me that it's still kind of viable to be protected? And if it returns true, then it is protected. There's reset protection where you say, I know that this is not reclaimed yet, not retired yet, so just like set the hazard pointer to that. It's like you don't need to check. Then you can also reset the protection to say we're done, like nullify the destructor will do that for you. Okay, make hazard pointer, that's the one that actually used to construct an actual owned hazard pointer. There's a swap. These are useful for overhand traversal. There's a move. It has move constructor and move operator, because that's quite useful. Because as I said, it takes 4 nanoseconds for construction destruction. Sometimes you don't want to construct something and then copy into it, or you shouldn't copy. Actually, I shouldn't say that. But I'm saying sometimes you need to move. So move is actually quite useful. All right. Now looking at the. Sorry. Oh, right. Looking at the IS interface, it's just like you will notice that all this clutter with domains is gone. So for now, until we hear from people say we want custom domains, then yeah, we can put them back in maybe a more meaningful way. But yeah, this is like you can see that domains are gone. All these functions that take domain or not, they are all simplified. So as you can see, and the same here, we have make hazard pointer. So that's the interface. The questions are, yeah, as I mentioned, do you want custom domains? Are the allocators sufficient, or like there's a better interface for that? Synchronous reclamation. When do you do you want something that is in the middle of a container being used, or actually you can say at the end? If you have a simpler requirement, there are more efficient ways to do it than the cleanup function that is offered here in the TS. Integrated commutative link counting, very useful. It's definitely I would recommend as follow-up for the IS. Non-intrusive retire. It's offered in Folly. Nobody used it, so okay, we'll see if anybody asks for it. User control is very useful, but we left it now as an implementation detail. Do you have a background thread or thread pool, executor, all this stuff? It's very important, but it's kind of we need to hear from because there are people on both sides of that. We don't want a thread, we want a thread. Okay, thank you for that. Michael, please. I hope I didn't take too much of your time.
Thanks, Magid. In case your mind is spinning over all this, believe me, we're talking about a lock-free algorithm, and you've heard of lock-free algorithms and how they're very important for high performance, for race-free execution, and for low latency. This goes beyond what most people mention as far as lock-free algorithm. It's lock-free end-to-end. That means that it's lock-free not just during the execution portion, it's lock-free during the reclamation, the retirement portion. That is really why it's powerful, and that's why so many people are using it for all of these different domains. I am going to go to something else that is also similar to this. It is also another lock-free algorithm, but it's an enhancement now on top of RCU and hazard pointer, and it's called asymmetric fences. Now, here's what happens. Now, there are many synchronization algorithms that have at their core basically a store load fence. And hazard pointers, most user space, RCU implementations, some types of work stealing, queues, or remodify write less, meaning mutexes that don't use remodify writes, they need something like this. So in some cases, the fence is required down a common path, but only to guard against a race with an uncommon path. So that is a waste. And so there's this idea of using an unbalanced and asymmetric fence. So in hazard pointers, the protect and the try protect path is common. Believe me, it is. I know if you don't remember, it is. And the reclamation path it protects against is uncommon because it's read mostly and write rarely, right? So, and similarly in read copy update, RCU, the RCU reader constructor path is common and the RCU synchronized path is uncommon. Other things, other examples like work stealing. If you have a work stealing queue, the owner that queue path is common, and the stealing that queue path is uncommon. You might have a load store mutex, for instance, that are not commonly used. However, with variants of asymmetric fence described, we're going to see how this is going to help. All it is that when you're a library author, you have this case where you might have to put a load store fence, which is the most costly kind, in a common path just to ensure safety against a race that is pretty rare in a very slow path. So when we do that, when library authors do that, it causes performance loss. And many systems go to great lengths on the fast path to have a lightweight fence. For example, Facebook's Folly, the open source library Folly uses a mem barrier system call on the writer and only a compiler barrier on the reader. And to see how amazing this is, you run this on a 2.5 gigahertz Haswell with using asymmetric barriers from this paper. So if it's a hazard pointer, you might use a has pointer holder protect and reset. If it's an RCU, you might use an RCU reader, construction and destruction. It's 2 nanoseconds, as opposed to 32 nanoseconds if you will replace those with a standard atomic thread fence with a memory order sequentially consistent. And if you have real workloads, they're even higher costs. So the proposal is actually pretty simple. This basically introduces synchronization primitives that are called heavyweight fences. And like fences, heavyweight fences and lightweight fences can have acquire semantics, release semantics, or both, or they can even be sequentially consistent. This is an example from the open source Facebook Folly library, where they basically have implemented the asymmetric thread fence according to this paper. Okay, you'll see that the lightweight fence, if it's Linux, it's just an ASM volatile memory. Otherwise, it's just an atomic thread fence, accepting whatever is the memory order. If it's a lightweight fence, it also does exactly the same thing, but except it calls the atomic thread fence with a different order. So the TS2, whenever we're doing a TS, we're always asking you guys to give us feedback in some ways, okay? And in this case, there's a lot of feedback the authors are asking. You know, should the asymmetric fence be no except? SG1 seemed to, we polled them, well, we didn't really poll them, I guess, but we said that they were leaning towards that, yes, it should be no except. And it was pointed out that if we make them no except for the TS, we'll find out if they should have thrown. If we don't make them no except in the TS, but should have been, we'll never get that feedback. So So are there any bugs that should be exposed by the formal modeling in practice? We want to find out if this is the right interface. Does it support an efficient implementation on a broad range of vendor platforms? Particularly interesting in this question for GPUs. Is this asymmetric fence useful for GPUs? How often is this feature used, for example? If it's not often, it's not actually worth standardizing, okay? Will this interact in surprising ways with other features like coroutines and executors and freestanding? And are there implementations where users might want an explicit options argument? For example, on Linux, you can take a sysmem barrier. All right, next one, byte-wise atomic mem copy. Now we're moving into the domain from high performance to what makes for safety and convenience. Anytime you're doing thread programming, multi-thread based one, you really do need to take some extra care about safety, okay? And the way this works is that this is just another mechanism to support low-cost, read-mostly synchronizations by protecting the shared data with an atomic sequence number. Now, byte-wise atomics basically allows individual byte atomics to be more efficient instead of making a large multi-byte all atomic, which can cause inefficiencies. Now, what this does is that it allows values that might be read while being written when it can be determined after the fact, this is a key, after the fact that a race did not occur. And one of the best example of that is sequence locks. So Maggot talked about reader-writer locks. Sequence lock is just a reader-writer lock that avoids writer starvation. And the way it does is that the writer increments the sequence number after the acquire lock and before the release lock, and then the reader reads the sequence number before and after reading the shared data. This is why it's after the fact you determine that there is no race. Okay? If either number is odd, then the writer had taken the lock while the data was being read, and it might have changed. If the numbers are different, then you also know that a writer has changed the data while it was being read. In either case, the reader has to retry in a loop until they read the same even sequence number, or alternatively, the reader just give up and simpler to some single try logs and whatever, right? So the proposal is that they propose to have introduced 2 additional versions of memcopy to do this, to resolve this, to solve this thing. It's a fairly common technique, basically, to implement low-cost read-mostly synchronizations. You basically have an atomic lock, an atomic load per byte memcopy, okay, and a atomic store per byte memcopy. We also have underneath the equivalence of what it looks like if you were to implement it. And after that, the sequence TS is also basically asking, does this cover enough of the use cases for speculative concurrent access? Or should we wait for a more comprehensive solution? Now, I have to say that we've tried comprehensive solution in the standard, and they were just too big. And this is basically narrowed down to the smallest solution that we can really solve. And that is basically to support sequence locks. There are other things that we could support, but once you expand, the solutions become bigger. And usually it's difficult to get that into the standard. We like to know if this is cheap to implement. We expect that on many platforms, this can be implemented as an alias on memcopy, because at least the non-inline version already basically satisfies our requirements, right? This is obviously a very low-level construct that probably is tolerated by most algorithms of interest. Okay, sorry, there's a low-level construct that is inherently error-prone, but it will. So the question is, will it be misused or in some unexpected way? Would it be useful to add an element size argument for samples? And will this also be used in the C compiler? Right? Last thing is called synchronized value. Again, this is for safety, okay? It's just something you could construct quite easily, but we like to package it up. And the reason it goes into TS is we don't know whether it would just be something that people would use a lot. So a synchronized value basically just wraps a value with a mutex-like control to control the access to the value so that you don't forget about the lock access and then unlocking it afterwards. Okay? Synchronized value of T stores a value of type T and a mutex, and then it exposes a pointer interface such that the dereferencing the pointer yields a special wrapper type that holds a lock to the mutex. And that can be implicitly converted to T for reading, and then you can forward any value assigned to the assignment operator for underlying T. Now it uses the apply interface, the apply function interface, and that's basically because it is similar, I forget which one it is, but essentially the apply function gives you a means of accessing the store value. It also is variadic, so it can operate on a set of value of set of objects. The name apply, oh yeah, that's right. It's applied, it's chosen because it's similar to a tuple or tuple. And since the operation is conceptually similar, so rather than expanding tuple to supply the argument to the function, the value wrapped by the synchronized values are basically extracted to give you the arguments to the function. And basically, this gives you an easy way for developers to ensure that all access to a given object are done with the relevant mutex locked. So in order to avoid simple mistakes when using synchronized value of T, there are no public member functions or operations other than the construction. And the actual implementation may use some alternate synchronization mechanism instead of a mutex, provided that the synchronization the requirements are met, like in spinlock, for instance. So this is what it looks like as a simple synchronized values example. This is a simple access that can be done with a simple lambda using the apply and passing in the lambda. And on the other side is a more complex processing that can be done with a more complex lambda or a separate function or callable object. And the TS2 is asking, should the synchronized value template be parameterized on the type of the lockable object? We already talked to say that it's defaulted to a mutex, okay? If they allow that, then this would allow the use with third-party or user-supplied mutex, and potentially, but it would complicate the interface. And then you might need a specialization for the default case. If the implementation wanted to use something other than a mutex, for instance, I would like to use a reader-writer lock instead of a mutex. But then we would definitely need a separate reader-writer operations in that case. Because right now, the interface is so simple with just the apply. If I want a reader-write, I would actually need a separate reader-writer, probably. Should we apply except, should apply except cons volatile qualify synchronized value of T arguments, as well as non-cons arguments? And this would again complicate the interface, but it would allow you to declare a cons synchronized value of T object reference. And that would allow you to guarantee that you can't change the stored value through calls to apply, which is something that I can imagine people would want. Can the mutex be a user mutex? So if that's the case, then it would need to be templated. Right now, it's not. All right, my final slide. You might have heard the question answer that some of this is already going into the IS C++26, even before the technical specification seeking feedback has been published. Well, the reason for, so you might say, why are you putting the cart before the horse? Well, it turns out that we collectively, Maggot and myself, were known as the low-latency brothers. We're just like the property brothers, they're just better looking and have more money, I think. But we've been working with this for better part of 10, 15 years. Since 2016, I am I'm now so old, I'm so old that I'm going to pass this to my children to try to standardize. Fortunately, the committee agreed that, yeah, we should just push this into C++26, even before the TS has been published. So it's actually already went through plenary in Varna in 2023, about 3 months ago. The final paper is already there. So there are a few things we are still seeking some feedback, and Maggot has mentioned that. But actually, really not much has changed from the TS to the IS. I think Hazard Pointer has more domains and things like that. And the synchronized reclamation thing was changed. That actually makes a lot of difference because when you go synchronize, it's expensive. I'm pretty much done. So a lot of people are already using this incredible low latency facility. The other three will probably have a little bit of easier time to be standardized because they're much smaller, but because they're new, they actually might not even make C++26, oddly. So for that, I'm done. Thank you. I'm going to ask my low latency brother to come on. And that's it. Thank you.
Yes, hello. Yeah, great talk. I'm very excited to have a lot of these features in the standard so I can stop writing them myself all the time. And then they won't be undefined behavior, because when I write them, they're undefined behavior. One question I have, actually, a question I have been getting a lot after my talk where I mentioned that I use hazard pointers is actually about low latency. So in the sort of like simplest vanilla implementation of hazard pointers, you would imagine that, you know, you do your cleanup by, say, every like 1,000 retires, which I think is the number hard-coded in Folly right now. You go and say, okay, that's enough retires. Now I'm going to go and do some cleanup, which, of course, in like the most vanilla implementation, that's a latency spike, right? Like you touched on this briefly during the talk, right? This means that a retire goes from a few nanoseconds now to probably like 20 microseconds to now go and clean up 1,000 things. And you mentioned, you know, there are ways around this, like you could hand off your cleanup off to a background thread or something. But are we going to have those kinds of options when it appears in the standard library, or are people still going to have to handwrite their own version of that?
That's a good question in what will happen in the standard, because in Folly, it's an opt-out having a separate executor for thread pool for reclamation. So that's like but then there were like in Folly, like there are users who actually insist on opting out. Good question about the standard. I would think there would be a decision by each library implementer, because the standard is not specifying what it does. It's not like one way or the other.
Right, because I imagine, you know, if the standard doesn't put something like this in, then low latency people will probably just avoid it, or they'll keep writing their own version.
I would say it's still low latency if, let's say, you're using it in a hash table and you're doing lookup. That lookup will be fast. It's just when you reclaim stuff and
only your stores have high latency potentially.
Just off the top of my head, maybe retire. You could just actually pass it to a background thread if you want. So if you really like, as in, I want to retire it, but I will not retire it because I don't want to be stuck reclaiming stuff. So I'm gonna give it to this other thread to actually retire.
You call retire on the background thread.
Yeah,
I see.
So maybe. How about that?
That's probably more expensive though than in the common case now.
But it's actually, my experience with the hash table is like, each reclamation is like, more expensive by like 20 nanoseconds, but then each lookup is way faster. So if it is read mostly, that kind of use case, then So.
Right, cool, thank you.
Oh, and by the way, you can't retire.
Hi, thank you. I have a few small ones, I hope. I'll let you after one. Okay, just a stupid question. Couldn't you use deleter for async retire? Like you have a deleter in there. Could you use that for async retire?
Yes. You mean custom deleter?
Yeah.
Yes. There are I've seen a lot of cases of using custom deleters. Yes. But for what?
Could you use that for async retire?
Did you hear that?
So
For what retire?
saying that during the reclamation, instead of actually deleting objects, you could hand the deletion.
Oh,
like
in
a
that case,
custom deleter.
that more like executor add or something. Like that. So this
Yeah.
is like not part of the
Yeah, but you
right?
so you have a customization point, a deleter. Could you that do asynchronous things?
So you have a custom deleter,
Yes.
and what's the question?
Could it, instead of deleting itself, send it off to background thread? Could that be the solution for the background deletion?
Maybe I haven't thought about, but yeah, okay, that's actually interesting thought. But it's cost. I would say using a custom deleter is like kind of now we're adding cost to the, so there are costs to that. But yeah, maybe not a bad idea. If someone wants.
Yeah, I had a few quick questions. Are the RCU domains, are those thread local? I forgot if you guys said that.
RCU domain in the proposal,
Yeah.
there is no custom, so it's not yet. If people ask for it, the RCU domain is just a name.
Oh, okay, yeah.
You use it to say, oh, I'm locking, because you cannot say I'm locking what. So you have to say I'm looking.
Okay, no, I was just wondering if
Yeah.
like the
But the
function,
implementation of lock and
like the
unlock
singleton function
is
returned
like-
a thread local or a global static, whatever.
Yeah, nothing global.
It's not global, so it is thread local. Sorry. Like the global,
I mean, there's a global structure to say, oh, I want to know where all these like
Yeah.
participant when you do synchronize. But
Right.
otherwise, when you're saying lock, you're actually, oh, I am locking, but actually I'm doing the work on a thread local structure.
Okay. My other quick question was, do the when you apply with the multiple synchronized values, is that like guaranteed to do like the lock the multiple mutexes in the non-deadlock way, or like?
Okay, so the question is when you apply multiple synchronized values, is that going to lock multiple mutexes and non? No, I don't. Yeah, yeah. I think that's one of the questions we want to get feedback on. Yeah.
Yeah. Because what if you have like two applies that they have different argument orders, and you don't want to get the bad deadlock? Yeah. Okay.
Great feedback. We need that feedback.
Yeah, so mine is mostly a comment because synchronized value is very, very close to my heart. I only discovered it a few months ago, and I've been using it very heavily. So it's kind of the opposite use case of what I guess you guys do, like writing really good code and making it run really fast.
Yeah.
So I've been taking over some code that's really poorly written, and there were a lot of threads and no locks whatsoever.
I don't know why people do that.
Yeah, but it happens, and then you have to add some safety quickly, and especially, well, actually both actually making it a safe and also doing it quickly is a really, really strong case for synchronized value because the compiler helps you, and it also helps you, especially when you're refactoring stuff. It's orders of magnitude faster with synchronized value.
Thank you for that comment. We have to stop here. Thank you very much. I'm glad there's so many questions. Okay.